Okay, at this point you should have already gotten through the intro to the 555 timer video. Now I want to go into the 555 timer specification. This specification is a little bit deeper, a little bit more to it than the transistor and the diode specifications that we've used before. But this one has the equations in it. It has a lot of great information that without this, there's no way you could even build a circuit using the 555 timer. So I want everybody to make sure they're using the right or the same one. So if you Google 555 timer, it's going to give you all the nice pictures of what it looks like and everything. If you go down, the one that you need to have is the LM555 timer datasheet Rev D from Texas Instrument. That's the one we want. Okay, if you click on that, it will bring it up. Now, I've already downloaded it to my desktop. That way I can highlight things and circle things as we go through this. Now, I'm going to preface all of this by saying you will have a short, probably 5-question quiz on this specification after you watch this video. That way I know, number one, that you've actually gone through it. But it is important. The specification is very important, as all of them are. All right, so let's get started to what this 555 does for us and how we can use the specification to do it. So let's look at some of the important things. Like I said in the intro video, we're going to do an A-stable and a monostable. Two different circuits. Similar, but they give us different outputs. Another important thing of the spec that you always want to look at are the different packages. We used the 8-pin dip when we did the flashy light soldering project, but in an application where you need something smaller, you can notice that the SOIC and the VSOP packages are almost half or a third of the size. So they do the same thing, they're just a different size or a smaller package. The other thing that we want to take heed of here is the pulse width modulation and the pulse generation. Those are really the two different things that we're going to be working on. We're going to make a free running A-stable, and then we're going to make a circuit that just gives us a pulse when we want it. The schematic diagram here, you need to understand exactly how this works. Totally joking, but you can see that all of the innards of that 555 timer is pretty much all transistors, okay? And it's just switching things on and off depending on what inputs it gets. So yeah, hard to understand, but actually pretty simple when you get down to analyze it. All right, this page here is probably one of the most important. This tells us our entire pinout for this chip. You'll notice it's and you learned this when you did the soldering project. In a U shape, it's 1, 2, 3, 4, 5, 6, 7, 8. U shape, just like this, giving you the U shape. Has that little notch at the top. That's how you know which one's which. And also you learn that it has to go in the proper way. Some of you reverse this when you put it in, which meant pin 5 was here and pin 1 was here, which was backwards. And obviously it didn't work. But these pins obviously are very important. This is what the inputs and the outputs all come from. Our VCC is just that. That's our battery voltage. Use a 9-volt battery. That's where you plug in the red. The black goes to ground. That's simple. Our trigger, when we talk monostable, it's that one that just had the quick pulse. Okay? That's what we use to actually trigger it. Now, how do we trigger it? If you look down here at the description, pin 2, responsibility for transition, yep, the output of the input depends on the amplitude of the, and actually that is incorrect. Well, they're just explaining it differently. Basically, we put a pulse on here, a negative pulse, and it will trigger the trigger that input. This is correct. It's just not the way I would have described it. The output is just that. Whatever we want on that output, whether it's a free running like this or the monostable, this is the pin that it comes out of. This is the pin we monitor to watch that signal. The reset is used to reset this entire chip. The negative pulse, as it says down here, the negative pulse applied to the pin will reset the timer. Okay, so if we never want to reset this, we would set this high because we do not want it to go negative. We want it to stay positive. And I'll show you that when we do the circuit. These two pins are what our R's and our C's are going to be attached to. That will determine whether it's a monostable, whether it's an astable, and it will also determine the length of our frequency and our period and all that kind of stuff. The control voltage, all we're going to do is we're going to tie a filter cap to this, to ground. That's pretty bad, but to ground and call it good. Okay? That's how we're going to handle that control pin. And again, all the descriptions are right here. I would make sure you go through and understand what it's meant by these. Plus, it also defines whether it's an input or an output, which is important also. All right, and the transistors and the diodes, we always went over the absolute maximums. Okay, when we talk about absolute maximums, that's exactly what we mean, absolute maximums. That doesn't mean that's where you want to operate this chip at. For example, if we go to supply voltage down here, it says that the absolute's 18 volts. Well, that's great, but we can't operate it continually at 18 volts. You'll destroy the chip, and I'll show you why in a little bit. But these are the absolutes. We do not want to operate at 18 volts, okay, for fear of damage. If we go down to the operating characteristics or the electrical characteristics, you'll see that the maximum is 16 volts, okay? So if you're asked by chance on a quiz, what's the operating voltage maximum, it would be 16. If you're asked the absolute maximum, it would be 18. Just throwing that out there. And then there's also our supply currents. These are important because if we put too much current into that chip or it draws too much, then we're in trouble. Our output, or the current that we want to supply, is going to be enough to light an LED, and we know what our LED maximum and minimums are, or at least you should. A couple other important things, the trigger voltage and the trigger current. Okay, when you do a monostable, we have to understand what those limits are, because we're going to be developing a circuit to turn that trigger on and off. And then our resets. Do we want to reset this circuit, or do we just want to tie it high? Well, there's our information for both trigger and reset. That's important stuff. Now, everything else on here I would say is as important, but for what we're going to do, this is what I want you to concentrate on. Those things there. Okay? That's the electrical characteristics. Oops, sorry. That's the electrical characteristics. Now, it also gives you some nice characteristic curves. We're not going to worry about those at this point. If we were in class, it'd be a lot easier. But if we go down to section 7.4, here's the great thing about this spec. Monostable operation, again, that's one of the circuits that we're going to build. And guess what? They actually give you the entire circuit. This is the monostable circuit. You don't have to design it from scratch. They give it to you. You'll notice that the monostable only has one R and one C. And by the way, this C is an electrolytic. We control that pulse that I mentioned in the intro with these two values. Okay? And I'll explain that in just a minute. Pin 5, I said earlier, we're just going to hang a filter capacitor off of that to ground, and it shows it right here. It's a 0.01 mic. It shows our output. It shows our trigger. Now, there's nothing hooked up to the trigger at this point. We'll get to that later. But this is where we will trigger this pulse. Our output shows two different loads. Now, it shows resistors with these dotted lines, but those dotted lines are basically telling us, well, you put whatever you want here. And as we've discussed in the past, resistors are essentially our components. So we could, at this point, put an LED right in here, and then when we triggered this and got this output pulse, it would light this LED for this amount of time, whatever length that pulse is. We'll then ask the question, what's the length of that pulse? Look right here. There's our equation to figure out the length of that pulse. T, the length of that pulse, is 1.1 times that resistor times that capacitor. And remember, that capacitor is an electrolytic. That's how easy that equation is. You got a little bit of multiplication there to figure out how long you want that. If you want that on for 5 seconds, then you pick an R and a C that gives you a time of 5 seconds. You hit that trigger, again, which I'll get to later. You hit that trigger, and that light right here will come on for 5 seconds. You want it on for 10 seconds, you want it on for 100 seconds, whatever, it doesn't matter. This is where you calculate that value with that T right there. Okay? So that's the monostable, and we're going to get into a lot more detail of that a little bit later. I would encourage you to read and the best you can understand this section of the monostable. Then come on down here and look at the astable. Again, in the spec, they completely give you the entire circuit. You don't have to redesign it. It's all right here. Notice it's wired a little bit differently. We don't use a trigger. In an astable, it's self-running. Again, that's a horrible waveform. But, so what we do is we have this trigger itself. So this is all the way over here tied to pin 8, and will trigger itself by doing that. We don't want pin 4, the reset is tied high because we don't want it to reset. But notice it has 2 resistors and 1 electrolytic capacitor. Again, that's an electrolytic. Same filter capacitor here. But how we determine what this period is and what our frequency is all determined by these 3 components right here. The equations for those are all down here. This is the one that you need to pay closest attention to. The frequency is equal to 1 over the period, which we already knew that, which is then equal to 1.44 over, there's 1R, there's the second R, and there's the electrolytic capacitor. That's the equation that we're going to be using when we do our 555 timer. I'm not going to require you to use these equations. Those are much more complicated and really need a lot of examples. I may shoot a couple videos at you to maybe to just get an idea of this. One other thing that we may pay a little bit of attention to when we get to astable is the duty cycle. The duty cycle is simply, if this is our cycle and there's our period, this calculates how much we're on. What is the time of this pulse right here? Which could be half of your period, it could be a little bit of your period, whatever. But we'll get to that when we get to astable. Okay? And a little chart down here. You can read a little bit more about it. But essentially, this equation right here is what we're going to use to create this circuit to give us a waveform like this. Now, real quick, if we put an LED right here, just like we did before on the monostable, with the monostable, it will just stay on for a period of time. Here you can see if we calibrate this right with the correct values, it'll give us a free running astable pulse, which will turn the light on, turn it off, turn it on, turn it off, turn it on, turn it off, at whatever frequency we define using these values by using that equation. All right, that's all I'm going to talk about on the spec. You will now have a 5-question quiz. Obviously, you're allowed to have this in front of you. I could time it. We'll see. We'll see what kind of mood I'm in when I do the quiz. But it should not take you very long. All right, that's the 555 timer. Go through this, make sure you understand it.